Recorded is rolling. It is Wednesday, May 6th, but we're continuing on this quantum mechanics journey. You guys have your journals out. And, where we left off the story is actually a really weird place. We're looking at Heisenberg's uncertainty principle, and then the double slit experiment, and then the Schrodinger's cat and the exponential problem. Right? I do have some alternate videos that are kind of short, a couple minutes each, so I'm going to roll those to bring you guys back into the fold here, and then we'll continue down this adventure.
Theory works, even though it shouldn't. And perhaps the ultimate proof of just how unsettling quantum mechanics can be is something called the double slit experiment. It will make you question whether reality exists at all. This simple configuration shoots particles of light called photons, one at a time, through two tiny slits in a screen.
With a laser which produces light, this light is attenuated such that only one photon at a time emerges. This photon passes through a two-slit assembly, and then we have a camera which registers the pattern behind the two-slit assembly. So what we see is that the photons arrive one by one on the screen, some here, some there, and it looks pretty random.
Since the photons travel one by one, some through this slit, some through that slit, you would expect them to leave a pattern of two stripes on the wall. And you would be wrong. They mysteriously create a band of stripes. This is what you would expect to see if a constant beam of light shined through the two slits. It would spread across the wall like a wave. So how can single bullet-like particles of light create a wave pattern? This could only happen if the particles go through both slits at the same time. In other words, the particle is in two places at once. But strangest of all is what happens when you put detectors next to the slits. When the photons are being watched, the wave pattern disappears. Take away the detectors, and the wave pattern comes back. This suggests that we can change the way reality behaves just by looking at it. Does this mean that reality itself is not real?
The modern answer is that the path taken by the photon is not an element of reality. We are not allowed to talk about the photon passing through this or this slit. Neither are we allowed to say that the photons pass through both slits. All this kind of language is not applicable.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrodinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrodinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I have answered, please?
Alright, here's new stuff. Quantum Zeno.
I've had a long, annoying day at work, running from one committee meeting to another. I come home with a pounding headache. I have an hour or so until Kate gets home, and all I want is a nap. Emmy is ecstatic to see me and does the happy dance all over the living room. Hooray, you're home! Yippee! She's wagging her tail so hard she almost loses her balance. This happens every afternoon when I come home. It's good to see you too. Let's do something fun. Let's play fetch. Let's go for a walk. Play fetch on a walk. Let's let me take a nap. She stops bounding immediately and looks crestfallen. Her ears and tail droop. No walk? Not right now, I say, lying down on the couch. Let me sleep for half an hour and then we'll do something fun. Promise? I promise. Now be quiet. The sooner I get to sleep, the sooner we'll do something fun. Okay. I lie down and get comfortable on the couch. I'm just starting to settle in for my nap when a cold, wet nose pokes me in the face. Are you asleep? No, I'm not asleep. Oh. A minute passes. Poke. Are you asleep? No. Another minute passes. Poke. Are you asleep? No. I sit back up, and I'm never going to get to sleep if you don't stop poking me with your nose and asking that question. Why not? Every time you poke me, you wake me back up. I have to start over again. If you keep waking me up, I don't get all the way to sleep, and you don't get to do anything fun. Oh. She brightens up. Hey, it's just like the zero effect. The what? You know, the paradox with the guy who can't catch the turtle because he has to go half the way to the turtle and then the next half of the way and then so on. And so he never gets anywhere. You mean Zeno's paradox. Zeno with an N as in nap. Zero Effect is a movie with Bill Pullman and Ben Stiller. Whatever, I don't spell so good. Anyway, what you're thinking of is the quantum Zeno effect. And yes, this is kind of like that. If you have a system that's moving from one state to another with the probability of being in the second state increasing over time, you can prevent the state change by repeated measurements. Every time you measure it to be in the first state, you restart the process. Right. So when I ask if you're asleep, I collapse your wave function back to the awake state, and you need to start napping again. Or you find yourself perceiving the branch of the wave function in which I'm awake again in the many worlds picture. But yes, that's the basic idea and a good analogy. I'm a philosophical dog.
Philosophical dog. Oh yeah. Okay, so it's related to collapse of the wave function, Schrodinger's equation, and I guess these last few would look at measurement problem, those experiment. Let's say you have this radioactive atom. Right? Now, lots of radioactive atoms have all different half-lives. Some are thousands of years, some are a fraction of a second. Look here, let's say just to throw a number at it, the half-life is like 1 hour. So if you left it alone and you come back 1 hour later, then there's a 50% chance that it should have decayed. Oh, if you come back 2 hours later, well, let's see, 50% times 50%, now there's only a quarter chance that it hasn't decayed, so it's a 75% chance of decay, right? But interestingly, if you have constant detection equipment on it, so constant observation, then that wave function continually collapses back to its original state, and this radioactive atom will never decay. So after say like 10 hours, you would say, well, like 2 to the power of 10, like it should almost certainly decay by now. Maybe there's a tiny sliver chance it hasn't. And yet, if you have this continual detection, continual observation, it just doesn't decay because the wave function keeps collapsing back to the original state. Right? In the graph here, I've got probability of decay as a function of time. Right? So, of course, after time, right, it should it's going to follow a curve like this that asymptotically approaches 100%. Okay? Except, of course, if you have detection equipment, and then it just hovers around zero continually. Okay, so quantum zero. Quantum zero.
Austin? Hello?
Yeah.
Why are you guys still talking? Oh, have I seen my multiple classes silent?
Hey, you guys got quantum zeno.
So the next one is good. We don't talk about. Oh, she wants to. I don't want to. It's just again, about that. That's his two. They really like his coffee. He's like the most. Take the last.
Let's do quantum tunneling.
Drop a ball down the side of a valley. Classical wisdom tells us that when the ball rolls up the hill on the other side, it can't go any higher than the height from which you dropped it. That's conservation of energy. Even if there's a nice big long slope to roll down on the far side of the mountain, the ball just can't get there, unless you give it enough energy to get over the barrier. But in quantum mechanics, things work a little differently. You see, the quantum world is probabilistic, so if you release a particle in a valley, chances are the next time you see it, it'll still be somewhere in that valley. But if there's a nice big slope to roll down on the far side of the mountain, well, that's a place the particle would really like to be. And it turns out there's also a small chance that's where you'll find it. If this isn't crazy enough, it's even possible you'll find the particle in the middle of the mountain. And in real life, this means that an electron sometimes hangs around inside the nucleus of an atom.
Some of us were taught in high school that the electron orbits around the nucleus, like a planet around the sun. However, this description has been understood as a gross misrepresentation for the better part of the last century. As it turns out, there is a characteristic uncertainty related to the very small. No one can tell exactly where something is. The best one can do is figure out where something is most likely to be. We can visualize this with something called a probability cloud. Here, we see the probability cloud of a proton at the center of a hydrogen atom. The denser regions are where the proton is more likely to be found. However, this uncertainty is not due to an inability of ours to measure the small in an exact manner. It is a fundamental aspect of the world in which we live, and its implications are extraordinary. Let us take, for example, the phenomenon of tunneling. If we can't tell exactly where something is, then it follows that we can't tell exactly where it's been, or where it will be. The best we can hope for is where it most probably will be. So there's a small chance that a racquetball thrown repeatedly at a barrier could just tunnel through the barrier, appearing almost magically on the other side. We don't see this often because a racquetball is pretty big and its uncertainty pretty small. But if we deal with matter on the subatomic scale, it becomes much more likely. Here our projectile approaches the barrier. We see here its probability cloud. Although it's most likely near the center of the cloud, we can see that there is a small chance of it being on the other side of the barrier. And so, sometimes, it is. Tunneling isn't a mathematical trick or an assumption. It's an observable fact. It's made use of commonly in modern electronics, and in a real way, allows for life on Earth. To see why, let us trace the creation of a photon in the sun. The light from the sun that we see reflected off the moon, the light which drives the Earth's weather, that provides the energy for life, all originates from the process of nuclear fusion in the sun. Two light atomic nuclei collide, forming a new element, and in the process, light is released. But these nuclei are both positively charged and so repel each other. Only if they have enough energy can they overcome this potential barrier and fuse. But if you do the math, the nuclei in the sun don't have enough energy. The sun's just not hot enough. Nonetheless, the sun shines, and it does so because of tunneling. Just like our physical barrier, there's a chance that our particles could be on the other side, and so the sun shines.
All right, it's pretty cool here. Okay, so remember from yesterday the existence of particles. There are particles, right? Kind of fuzzy, right? And probabilistic. It follows that Schrodinger equation, right? Until of course you make a measurement, then that wave function collapses, and so on, right? But things don't exist in like definitive points, like in Newtonian physics. Like, okay, well, this definitely has a mass and a location that you have to map out. And so down the atomic scale, things are a bit fuzzier. So the best you can do is have like maybe a probability cloud. So take that Schrodinger equation, imagine in 3D, to be like sort of a fuzzy cloud shape. And it's probably going to be somewhere near the center, but probability. But it could be somewhere near the periphery. Right? So you have some barrier here. I'd say like if you have a hydrogen and a hydrogen that normally would not fuse, well, sometimes they'll jump this barrier, and sometimes they will fuse into making helium. Right? And that was one of the applications of this. It could help explain some of the nuclear fusion in the sun. Right? The nuclear fusion in the sun. Okay. This is to say, if you calculate what's the temperature and the pressure at the center of the sun, that would initiate this fusion. Doesn't seem to quite add up, right? Until you also account for quantum tunneling. Right? Modern electronics. So, if you guys remember Moore's law, while you guys are copying that, see if I can find Moore's law. Oh no, sorry, take all my posters down. Go with that. But I think I mentioned that to you before. If you count how many transistors can you economically fit on a computer chip over decades, it periodically doubles or follows an exponential curve, right? And yet, if you make things smaller, 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 at some point you're going to run into this effect where how do you store zeros and ones on well, how small can you get? Maybe electrons or something. But at some point, if you run into tunneling, you kind of run out of space to work with. Right? So Moore's law might have an inevitable into it just because of that. As long as it's just small, maybe you can make it a chip. Okay, it's an idea anyway. All right, you guys ready for entanglement? All right. Okay. Here, I'll set up this next one a little bit. So, do you guys remember we just covered relativity about a week ago, theory of relativity? And remember how nothing can move through space faster than the speed of light? Okay. And if you follow those relativity equations, then if you were to travel faster than light somehow, well, you're crossing over a vertical asymptote on the graphs. And you show that some cases you might make the case that like time is moving backwards or something weird. Right? So nothing can move through space faster than the speed of light. Okay. Now there are a couple of like kind of weird exceptions to this. One has to do with universal expansion. If you look at very, very, very distant galaxies from us, and there are galaxies almost certainly beyond those, galaxies can move away from each other faster than the speed of light if you get far away enough, but they're not actually moving through space faster than the speed of light. What's happening is that space is expanding between them, right? So that's okay. Okay, kind of a weird exception there, right? And another weird exception has to do with this quantum entanglement, right? Now, this next video I'm going to play for you guys is a little longer and a little more technical than some of these, but yeah, I think it's worth seeing some of these too. Got a Veritasium video for you guys, okay? But yeah, follow as best you can, and this one's good to think about deeply here. Hey, guys, ready for entanglement? All right, here we go.
In the 1930s, Albert Einstein was upset with quantum mechanics. He proposed a thought experiment where, according to the theory, an event at one point in the universe could instantaneously affect another event arbitrarily far away. He called this spooky action at a distance because he thought it was absurd. It seemed to imply faster-than-light communication, something his theory of relativity ruled out. But nowadays, we can do this experiment, and what we find is indeed spooky. But in order to understand it, we must first understand spin. All fundamental particles have a property called spin. No, they're not actually spinning, but the analogy is appropriate. They have angular momentum, and they have an orientation in space. Now, we can measure the spin of a particle, but we have to choose the direction in which to measure it. And this measurement can have only one of two outcomes. Either the particle's spin is aligned with the direction of measurement, which we'll call spin up, or it is opposite the measurement, which we'll call spin down. Now, what happens if the particle's spin is vertical, but we measure its spin horizontally? Well, then it has a 50% chance of being spin up and a 50% chance of being spin down. And after the measurement, the particle maintains this spin. So measuring its spin actually changes the spin of the particle. What if we measure spin at an angle 60 degrees from the vertical? Well, now, since the spin of the particle is more aligned to this measurement, it will be spin up 3/4 of the time and spin down 1/4 of the time. The probability depends on the square of the cosine of half the angle. Now, an experiment like the one Einstein proposed can be performed using two of these particles, but they must be prepared in a particular way. For example, formed spontaneously out of energy. Now, since the total angular momentum of the universe must stay constant, you know that if one particle is measured to have spin up, the other, measured in the same direction, must have spin down. I should point out it's only if the two particles are measured in the same direction that their spins must be opposite. Now, here's where things start to get a little weird. You might imagine that each particle is created with a definite, well-defined spin. But that won't work, and here's why. Imagine their spins were vertical and opposite. Now, if they're both measured in the horizontal direction, each one has a 50-50 chance of being spin up. So there's actually a 50% chance that both measurements will yield the same spin outcome. And this would violate the law of conservation of angular momentum. According to quantum mechanics, these particles don't have a well-defined spin at all. They are entangled, which means their spin is simply opposite that of the other particle. So when one particle is measured and its spin determined, you immediately know what the same measurement of the other particle will be. This has been rigorously and repeatedly tested experimentally. It doesn't matter at which angle the detectors are set or how far apart they always measure opposite spins. Now just stop for a minute and think about how crazy this is. Both particles have undefined spins, and then you measure one, and immediately you know the spin of the other particle, which could be light years away. It's as though the choice of the first measurement has influenced the result of the second faster than the speed of light, which is indeed how some theorists interpret the result. But not Einstein. Einstein was really bothered by this. He preferred an alternate explanation, that all along the particles contained hidden information about which spin they would have if measured in any direction. It's just that we didn't know this information until we measured them. Now, since that information was within the particles from the moment they formed at the same point in space, no signal would ever have to travel between the two particles faster than light. Now, for a time, scientists accepted this view, that there were just some things about the particles we couldn't know before we measured them. But then along came John Bell with a way to test this idea. This experiment can determine whether the particles contain hidden information all along or not. And this is how it works. There are two spin detectors, each capable of measuring spin in one of three directions. These measurement directions will be selected randomly and independent of each other. Now, pairs of entangled particles will be sent to the two detectors, and we record whether the measured spins are the same, both up or both down, or different. We'll repeat this procedure over and over, randomly varying those measurement directions, to find the percentage of the time the two detectors give different results. And this is the key, because that percentage depends on whether the particles contain hidden information all along or if they don't. Now, to see why this is the case, let's calculate the expected frequency of different readings if the particles do contain hidden information. Now, you can think of this hidden information like a secret plan the particles agree to, and the only criterion that plan must satisfy is that if the particles are ever measured in the same direction, they must give opposite spins. So, for example, one plan could be that one particle will give spin up for every measurement direction, and its pair would give spin down for every measurement direction. Or another plan, plan 2, could be that one particle could give spin up for the first direction, spin down for the second direction, and spin up for the third direction, whereas its partner would give spin down for the first direction, spin up for the second direction, and spin down for the third direction. All other plans are mathematically equivalent, so we can work out the expected frequency of different results using these two plans. Here, I'm visually representing the particles by their plans, their hidden information. With plan 1, the results will obviously be different 100% of the time. It doesn't matter which measurement directions are selected. But it does for particles using the second plan. For example, if both detectors measure in the first direction, particle A gives spin up, while particle B gives spin down. The results are different. But if instead detector B measured in the second direction, the result would be spin up. So the spins are the same. We can continue doing this for all the possible measurement combinations, and what we find is the results are different 5 out of 9 times. So using the second plan, the results should be different 5/9 of the time. And using the first plan, the results should be different 100% of the time. So overall, if the particles contain hidden information, you should see different results more than 5/9 of the time. So what do we actually see in experiment? Well, the results are different only 50% of the time. It doesn't work. So the experiment rules out the idea that all along these particles contain hidden information about which spin they will give in the different directions. So how does quantum mechanics account for this result? Well, let's imagine detector A measures spin in the first direction and the result is spin up. Now immediately you know that the other particle is spin down if measured in the first direction, which should happen randomly 1/3 of the time. However, if particle B is measured in one of the other two directions, it makes an angle of 60 degrees with these measurement directions. And recall from the beginning of this video, the resulting measurement should be spin up 3/4 of the time. Since these measurement directions will be randomly selected 2/3 of the time, particle B will give spin up 2/3 times 3/4 equals half of the time. So both detectors should give the same results half of the time and different results half of the time, which is exactly what we see in the experiment. So quantum mechanics works, but there is debate over how to interpret these results. Some physicists see them as evidence that there is no hidden information in quantum particles, and it only makes sense to talk about spins once they've been measured. Whereas other physicists believe that entangled particles can signal each other faster than light to update their hidden information when one is measured. So does this mean that we can use entangled particles to communicate faster than light? Well, everyone agrees that we can't. And that is because the results that you find at either detector are random. It doesn't matter which measurement direction you select or what's happening at the other detector, there's a 50-50 probability of obtaining spin up or spin down. Only if these observers later met up and compared notebooks would they realize that when they selected the same direction, they always got opposite spins. Both sets of data would be random, just the opposite random from the other observer. That is indeed spooky, but it doesn't allow for the communication, the sending of information from one point to another faster than light. So it doesn't violate the theory of relativity. And that, at the very least, would make Einstein happy.
Alright, so here's a real weird one. Alright, so we've got these entangled particles. They have this angular momentum, or call it spin. Okay? And if you entangle the particles and then pull them apart, then they must always necessarily have opposite spin from each other, so that angular momentum is conserved in the universe. Okay? If you measure one at spin up in the vertical axis direction, then the other one will 100% of the time be spin down. Okay, so no surprise there. Okay? But the spins are not well defined. It's not like, oh, if I throw a baseball and I make it a curveball, there's clearly an axis that it's rotating about. Okay? And quantum mechanics, it gets a little fuzzy, probabilistic, okay? Until, of course, you measure it, and then it maintains that direction keeps going. Okay? But once you measure it, and say the wave function collapses, and it's definitely spinning along one axis, okay? Then you immediately know the other must be the opposite. Interestingly, if you separate these by some distance, then it seems like there's updated information faster than light. Okay. Now, for a long time, but say Einstein thought, going into well, Einstein died, I think, in the 1950s, so that was before this experiment. You think, well, maybe there's some information that we just don't have access to be able to understand yet, or nobody's quite thought about yet, or knows how to measure. Right? It must be some kind of hidden information that must be explaining this. Okay? But then John Bell comes up with this experiment in 1964 that took up most of that video that you guys saw, where splits these directions by 120 degrees, right? And you do all that math of the probability and the cosine of the angle, right? And you get a really weird outcome from this, which is that it's looking more and more like, yes, the spin information is locks in place and updates instantaneously from one to the other, like as soon as you measure one, right? But instantaneous would be faster than the speed of light. So that, at least at the outset, does appear to violate theory of relativity. Right? But then there's one more catch to that, which is that this is random information. So could you send an email from here to the moon in less than a second, which is faster than light can travel, right? Using quantum entanglement somehow. And seems to be everybody says, well, actually, no, you can't do that because like even if you have like ones and zeros, you turn this into ones and zeros in binary code, and maybe everyone send an email, right? Well, you can't do that because this is random information. You don't actually know what the outcome is going to be before you make the measurement. So there's no way to send useful information, say, across the universe using this method. Okay, so quantum entanglement. All right. All right, you guys got entanglement in your journals. Your journals. You guys good?
Newtonian determinism says that the universe is a clock, a gigantic clock that's wound up at the beginning of time, and it's been ticking ever since according to Newton's laws of motion. So, what you're going to eat 10 years from now on January 1st has already been fixed. It's already known using Newton's laws of motion. Einstein believed in that. Einstein was a determinist. Well, does that mean that a murderer, this horrible mass murderer, isn't really guilty of his works because it was already preordained billions of years ago? Einstein said, well, yeah, in some sense that's true. Even mass murderers were predetermined. But he said they should still be placed in jail. Heisenberg then comes along and proposes the Heisenberg uncertainty principle and says, nonsense. There's uncertainty. You don't know where the electron is. It could be here, here, or many places simultaneously. This, of course, Einstein hated because he said God doesn't play dice with the universe. Well, hey, get used to it. Einstein was wrong. God does play dice. Every time we look at an electron, it moves. There's uncertainty with regards to the position of the electron. So what does that mean for free will? It means in some sense we do have some kind of free will. No one can determine your future events given your past history. There's always the wild card. There's always the possibility of uncertainty in whatever we do. So when I look at myself in a mirror, I say to myself, what I'm looking at is not really me. It looks like me, but it's not really me at all. It's not me today, now. It's me a billionth of a second ago, because it takes a billionth of a second for light to go from me to the mirror and back.
Great. So if you take the principles that you learned in this class before this week, so going all the way back to August, there's a deterministic implication. Right? So here I have an analogy with, say, playing billiards. Say you got this cue ball, I'm gonna strike the cue ball with the stick, and it's gonna like bounce into this ball, and you're all gonna bounce around. Right? As soon as I strike the cue ball, what's gonna happen in the next few seconds is effectively determined. Okay, and if you know how to solve collisions with conservation of momentum, and you use some trigonometry, because this would be a two-dimensional example. We got a two-dimensional plane surface. Right? You can know where the ball is going to bounce and where it's going to end up, and maybe you can get really good at billiards and make the balls in the pockets and the whole way. Right? Well, if you think about it, how would that not necessarily apply to all material and all matter? Right? So if you get down to like objects are made out of atoms, right? And maybe atoms could follow these laws just like the billiard balls do. Right? So when, say, like, two objects collide, or there's some kind of interaction, or right, experience some force, right? And how far out could you determine, right? And if you thought that you had some kind of free will, then how could you possibly break from this? Because, well, your brain is made out of material or out of matter. Right? How do you determine when you get hungry or when you get tired? Well, those are all biological processes that have to do with the chemistry in your body and in your mind. Right? So how far does this go? How much free will do you actually have versus how much is predetermined? Okay? And if you follow Newtonian mechanics to its logical end, it would seem like, well, maybe there's no such thing as free will at all, even though it might feel like there is, but maybe there isn't. Okay. And in physics, we basically got these two models. We got the Newtonian model, which the updated version is Einstein relativity. Right? But then we got this other model, which is quantum mechanics, what we're doing now, which is more probabilistic, things that can't be certain. Right? There's another perspective on this, which is maybe if you have emergence, like some kind of emergent property, or maybe there's something there that doesn't necessarily follow determinism. Right? Or maybe there's some aspect of the universe and consciousness that doesn't even fit squarely in either of these camps either, that we don't have a good way to quantify or measure or understand. Right? So kind of an open question there. But if you look up experiments about free will, it can get kind of spooky how little free will maybe have compared to what it feels like you have. But yeah, so more of an open question there. All right. Oh, here, I'll just do 4 fundamental forces with you guys here. So they're considered, most physics textbooks, you open them up, they're considered to be these four fundamental forces. So let's do this one. Okay, so one of them is gravity, right? Gravitational force. It's like the Earth pulling you down and holding you in your seat right now. Right. Although, if you remember back about a week ago, there's a perspective from general relativity that claims that, well, maybe gravity isn't actually a force at all, right? But you have to go back to last week. I played you guys a Veritasium video. You made a really good case for that. Anyway, I'm just going to throw it in this list anyway. Right, there's electromagnetism, electromagnetism. And in a typical physics 1 class, these are the main two forces you care about. Okay. So electromagnetism, obviously electricity, magnetism, anything like that. Okay. But also here, what if I just like pick up this object or pick up a pen? Right? What force is involved there? And those are contact forces. Hey, isn't this pen made out of atoms and my hand is made out of atoms? And on the outside of atoms are these electron fields, these electron shells. So it's electrons against electrons, and it's you apply that repulsive force. So any kind of contact force, like me picking up something, setting something on a surface, right, a normal force, a friction force, that's all under this umbrella of electromagnetism. Okay? Now the other two forces are, let's see, strong nuclear force. And that's considered to be responsible for holding the nucleus of an atom together. Otherwise, why would all the protons hang out at the same place? Why would protons group with protons and hang out in the nucleus together? Right? From an electromagnetic point of view, no way do they want to do it. They all want to repel because they all have the same charge. Like charges want to repel, right? And gravitational force is actually the weakest of all these forces. Again, if you even consider this to be a force, right? These other three forces are way, like many order magnitude stronger. So gravity can't account for protons hanging out together. So what is, right? We'll call that a strong nuclear force. Right? And the fourth fundamental force in the universe is it's called the weak nuclear force. And that's related to radioactive decay. So eventually, I think we'll run into an example of like carbon-14 dating. Right? So anything that's radioactive that has a certain half-life associated with it, it's a matter of time before it radioactively decays into a different kind of atom. Right? Like carbon-14 will eventually decay into nitrogen after about 5,000 some hundred years. Okay, so there you go. There's considered to be the four fundamental forces in nature, okay, and that is a good segue to standard model of particle physics. All right, you guys ready for standard model?
The objective of particle physics is to understand the basic structure and laws in nature, all the way from the largest dimension in the universe, formation of galaxies and stars, all the way down to the smallest dimension in the microcosm.
So historically, we knew about all of the different elements in nature. We knew about helium, hydrogen, oxygen, gold, lead, and so on, which are all made of different atoms. But a great simplification was made when we realized all the atoms are just made out of three particles, the protons, the neutrons, and the electrons. And just by adding more protons, more electrons, we get the different element, different type of atom.
In principle, you can build a very simple universe with just protons, neutrons, and electrons.
But it became much more complicated in the beginning of the 20th century when we found many, many new particles from cosmic rays.
There wasn't really a system established to organize this zoo of particles.
So we were calling these new particles things like pi, sigma, delta, and so on. And things got so bad, we were running out of symbols to name these particles. So we started organizing these particles according to the properties they have. And the properties are things like spin, electrical charge, so if they're positively charged, negatively charged, or neutral, mass of the particles, and the lifetime of the particles, which is how long it takes before they decay into lighter particles.
To simplify the picture, new fundamental particles called quarks were predicted. and the whole zoo of particles could be described by combinations of these quarks. And this was the birth of the Standard Model. At the beginning, there were only 3 quarks. Then a 4th, 5th, and 6th quarks was predicted and then discovered, and this gave us great confidence in the model. In addition to these quarks, there's another set of fundamental building blocks of matter, the so-called leptons. They are composed of an electron, their heavier cousins, the muon and the tau, and their neutrino partners. In addition to the fundamental building blocks of matter, the Standard Model also incorporates the fundamental forces. The exchange particles of the weak force are the W and the Z boson. The weak force explains the energy production in the sun and is responsible for the radioactive beta decay. The electromagnetic force acts on charged particles. The corresponding force carrier is the photon. The electromagnetic force is responsible for propagation of light or for the fact that a magnet can pick up a paperclip. The strong interaction acts on the quarks. The corresponding force carrier is the gluon. The gluon literally glues together the quarks in the neutrons and the protons, and it holds the nucleus together.
All right, he's going to talk about this Higgs boson. Now, at the time this video was released, they hadn't quite discovered it. This is kind of an outdated video, right? But then they go on to say, like, this is kind of a messy model, right? Because you've got these 17 elementary particles. Why 17? Why is it organized like this? Right? And what does it have to do with, okay, like beyond the model, a lot of these other mysteries in the universe, like dark matter, you guys saw a week or two back, right? How about some of these other, what about extra dimensions? Right? So, how does it tie this? So there's still a lot of mysteries in the universe. Right, so the Standard Model of particles, let me show you guys what this actually looks like laid out. Zoom out a little bit here. It's a little better, right? So, this looks kind of like the periodic table in chemistry, doesn't it? You guys remember periodic table? There's like 100 and some elements, right? But to particle physicists, this is sort of the analogous counterpart here. There are these 17 elementary particles, right? And really only 12 of these are fermions, and then these 5 pink ones on the right are these bosons. Right. Yeah, so they're organized by mass, charge, and spin. Okay. And the most recently discovered one, back in 2012, I think it was, is this the Higgs boson. Right? When I say discovered here, there's a whole story behind that too that we're going to cover. But yeah, right. A lot of these were uncovered mathematically. The Standard Model goes back to, I think, the 1970s. Right? But then, of course, in science, you want to do experimental testing and empirical measurement. So they needed a particle collider for that. Okay, and we're going to go to the Large Hadron Collider after this. Okay, so Standard Model particle physics. Okay, got these 17 elementary particles that are organized by mass, charge, and spin. Okay, they've organized these into quarks, leptons, and bosons. Okay. Now, if you think about elements on the periodic table, you can reduce those to some combination of protons, neutrons, and electrons. Okay, so what are those in terms of these? Okay. So a proton turns out to be 1 up. Sorry, 2 up and 1 down quark. A neutron is 1 up and 2 down quark. Right? Protons and neutrons have nearly identical masses, although they are slightly different. And then an electron actually does show up as one of these elementary particles, even on the Standard Model. So an electron is elementary. Right? Although the universe and matter is more than just up, downs, and electrons. Right? There's also lots of other particles too. Okay. So what have we got here? We got the charm, we got tops, we got strange, we got these different neutrinos. There's a photon here. A photon is one of them. Right, we're about to be looking at the Higgs. Got all these. Okay, we only have about 3 minutes, so I'm going to close down this video here, but we'll pick up this story here another day.